Okay, let's dive into this. Welcome to today's explainer. You know those chips running your smartphone, your car, and basically our entire modern lives? Well, today we're looking at the blueprint for Nanhua University's International Semiconductor Credit Program. And honestly, unpacking this was a massive eye-opener. We're not just talking about a breakdown of a college major here. It's more like the architecture of a global talent pipeline, a system purposely designed to train the next generation of engineers who are going to literally build the future of computing, AI, and global supply chains.
Here is our roadmap for today. We're covering the global talent pump, mastering the supply chain, speaking the industry language, managing projects and yields, building a green industry, and finally, bridging academia and industry. All right, let's get right into it.
Section 1. The Global Talent Pump, Connecting Regions for Industry Growth. Now, what's really interesting here is this term, talent pump. We usually think of logistics when we're talking about shipping parts or raw materials, right? But this is a global logistics platform for human capital. It's a highly structured system that actively draws in raw potential, refines it through intensive training, enables global mobility, and then strategically drops those highly skilled pros right into the industries that desperately need them. And it's just fascinating to see how this operates across three massive geopolitical zones. Just imagine the sheer scale of this trilateral flow for a second. We kick things off in Southeast Asia, which is this crucial emerging talent pipeline just packed with eager, capable students. Then that talent flows right into Taiwan, and Taiwan serves as the advanced training ground. I mean, it's not just a classroom, it is the ultimate semiconductor cluster. It gives students an unmatched environment to learn the entire industrial chain. And finally, we've got the United States, which acts as the destination for further academic pathways, high-level internships, and critical industry placements. It's just this perfect, continuous loop of recruitment, training, and global placement.
Section 2. Mastering the supply chain, from raw silicon to advanced integration.
So, to really master the supply chain, you've got to understand this massive divide. On one side, we have the front end, or the fab process. This is where raw silicon wafers are actually transformed into integrated circuits. We're talking staggering precision, super complex chemical processes, and massive financial investments. This has always been the traditional powerhouse strength of the Taiwanese foundry model. But here's the real plot twist for me, the back end. This used to just be about slapping a plastic case on a finished chip. Well, not anymore. Today, advanced packaging and final testing are the absolute new frontiers for high-performance computing. It's totally critical for heterogeneous integration, which is basically just a fancy way of saying stacking different chips together to power modern AI. And as it turns out, to be a globally competitive engineer today, you've got to master both sides of this divide.
Let's move on and see how this builds, because understanding the physical, step-by-step reality of actually making a microchip is just mind-bending. Step 1 is lithography. This is where they use extreme ultraviolet light to print microscopic patterns. To put that into perspective, we are talking about transferring features smaller than a single virus. No way, right? Step 2 is etching, where plasmas meticulously remove specific materials to carve out the 3D structural design. Then we have Step 3, deposition, which involves growing critical, functional thin film layers, often literally atom by atom. And finally, Step 4 is chemical mechanical planarization, or CMP, which uses chemical slurries to perfectly smooth and flatten the wafer surface before adding the next layer. It's an absolute marvel of modern engineering, and students are in there mastering every single one of these impossibly small steps.
Section 3. Speaking the industry language. Linguistic tools for engineering success.
And this brilliantly illustrates something you might not expect. Being bilingual in this industry, it's not about ordering a coffee or asking for directions to the train station. It's hardcore engineering. Professional Mandarin is specifically required for navigating the incredibly dense, fast-paced foundry clusters in Taiwan. Then there's semiconductor Japanese. Why Japanese? Well, because Japan holds a massive, dominant position in supplying crucial high-tech equipment and specialized chemical materials. I mean, if you're trying to solve a critical equipment failure, you need to be able to read Japanese technical manuals, not just exchange conversational pleasantries. And finally, technical English is basically the bedrock for managing international project standards and complying with U.S. academic pathways. Because the reality is, knowing everyday vocabulary completely falls apart when you're trying to explain a microscopic defect in a thin film deposition process to a supplier in Tokyo or a fab manager in Hsinchu. I was so fascinated to learn that this program focuses entirely on practical, cross-cultural communication designed to solve actual manufacturing problems. It's not just textbook vocab, it's about surviving and thriving in the global supply chain, using language as a literal precision tool.
Section 4, Managing Projects and Yield, the Business of Making Chips.
Just imagine being the manager who has to explain to a board of directors that a microscopic speck of dust just evaporated $1 million. Ouch, right? That's exactly why yield dictates everything. As the quote says, in semiconductor projects, yield is not only a technical issue, but also a management issue. Yield is simply the percentage of perfectly functioning chips you actually get from a wafer. A tiny technical flaw, a speck of dust, or even a slight chemical imbalance means the absolute difference between a highly profitable quarter and catastrophic financial losses.
So, what happens when yield drops? Engineers immediately deploy root cause analysis. And honestly, looking into this, I realized it's essentially high-stakes detective work. How exactly do you track down a microscopic defect on a silicon wafer that is costing millions of dollars an hour? Is it a metallic contamination? Was it a scratch from a CMP pad? Or maybe an issue with the photoresist? Students are trained to systematically run this ultimate diagnostic process to identify the exact origin of a failure way before it turns into a massive, uncontainable risk.
And to actually pull that off, they have to navigate an absolute maze of management constraints in real-world fab environments. They aren't just tracking defect density to measure manufacturing risk or using a risk matrix to balance severity against likelihood. Oh no. They are juggling rigorous cost and schedule control because in this industry, time is literally money. Simultaneously, they're executing change management when project requirements suddenly shift, all while navigating relentless supply chain constraints so critical materials never run dry. Honestly, it's like playing project management on extreme difficulty mode.
Section 5, Building a Green Industry, Sustainable Semiconductor Manufacturing. So the crucial point here is that environmental responsibility is no longer optional in this field. It's a strict baseline for global operation. Students are trained to rigorously audit the product carbon footprint across 3 standardized scopes. Scope 1 involves tracking direct greenhouse gas emissions right from the fab's own process gases. Then Scope 2 requires managing the massive, indirect emissions generated by the incredible amounts of purchased electricity needed to run a fab 24/7. But Scope 3? That absolutely blew my mind. It's like the ultimate boss level of environmental auditing. It involves calculating complex emissions across the entire global supply chain. I mean, imagine trying to track the carbon footprint of a ship carrying raw silicon halfway across the world, all the way to the final shipping of the packaged chips. On top of that, you have to aggressively manage specific, highly potent gases used in front-end processing. We're talking nitrogen trifluoride, sulfur hexafluoride, and perfluorocarbons. I actually learned that these have incredibly high global warming potentials, so modern semiconductor professionals are trained to implement local scrubbers right at the equipment level. They literally have to destroy these emissions before they ever have a chance to reach the atmosphere, achieving an exceptionally high destruction and removal efficiency. Section 6. Bridging Academia and Industry, from the classroom to the clean room. So how does this talent pump actually turn on? Well, students don't just sit around in a classroom absorbing theory. They are stepping directly into actual functioning fabs through corporate and overseas internships. They benefit from dual degree systems and cross-national credit certification, which means their education is instantly globally recognized. They spend their time executing capstone projects centered entirely around real, unsolved industry challenges, all guided by active industry mentorship that links theory to active problems. And crucially, they graduate with verifiable sustainability certifications like ISO 14064-1, basically guaranteeing they are day one ready to solve problems in the global supply chain. We've seen the sheer technical depth, the cross-cultural language requirements, the fierce project management, and the absolute crucial push for sustainability. Nanyang University has laid out a super clear, structured blueprint connecting Southeast Asia, Taiwan, and the United States. The demand for these multifaceted professionals has literally never been higher. So I'll leave you with this final thought. As the world races toward an AI-driven future built on silicon, are you ready to enter the global semiconductor talent pump? Thanks so much for joining me on this explainer, and keep learning.